So as Dr. Wayne said, we are Team Smart Sleep, a smarter baby sleep monitoring system for sudden infant death syndrome, also known as SIDS. So our goal is to design an advanced baby sleeping monitor to prevent any possible chance of SIDS. For those who don't know what SIDS is, it is the sudden and unexplained death of a baby within their first 1 to 2 years of life. After years of research and collected data, it's been found that SIDS is not it doesn't lead to one direct factor, but rather a combination of three factors, such as the vulnerability of the infant, their early stage of development, and the outside stressors that lie in its surrounding environment. So, by using real time data collection and analysis, we can detect these outside stressors and collapse one of the three converging threats that can lead to SIDS. I am Paolo Costelli. I am a computer engineer and the software specialist in this project.
I am Alexander Spinelli, the team leader and a software specialist.
I'm Jonathan Elias. I'm the hardware specialist and electrical engineer.
And Chris is the hardware specialist.
So, our project motivation. It is found that 63% of sudden unexpected infant deaths within the infant's first 2 years of their life is due to two causes: SIDS and suffocation. So, as a parent, we all know there's nothing more important to than their child's health. So, our device will ultimately help to detect, alert, and mitigate any outside stressors that can cause suffocation, as well as monitor their sleep to create a safer environment for the infant when they're not under a direct monitorization from their parent. So to the right, you can see our design for a fully functioning baby sleep monitor to help combat SUID. We planned to utilize the sensors to monitor the baby and its surrounding environment and alert the parents if there's any potential danger to the baby. The collected data from the sensors can be presented in real time to the parents through a mobile application and can be used to further research any leading factors to research towards SIDS. The parents will be able to gain an analytical insight and real time data to better visualize and understand their infant's health, as well as sort of recognize any sleeping patterns and making sure that nothing is out of the ordinary for the baby's health. Our system begins with the sensors collecting data, which is then processed through the microcontroller. The microcontroller communicates all of the real-time sensor data to the application via Bluetooth Low Energy, or BLE. The mobile application then performs data analysis on the edge and sends the data to a cloud database for storage. The cloud database and the mobile application are in constant communication throughout the entire project to ensure that the user or the parent is provided with present as well as previously recorded data from the sensors. So a large focus on mitigating SIDS is by detecting these outside stressors implemented as alerts. So when the sensors collect data that is higher or lower than the comfortable value that we want for the baby, it will send an alert to the parent to make sure to check up on their child and make sure that everything is fine.
Sorry about that. Okay, so the information will be sent through basically like a gap profile, and that'll have the different services that we're using. The services are basically the different sensors that we have: temperature, oxygen, heart rate, the accelerometer, and I forget what the last one is. But yeah, those are basically the services and or the characteristics. Basically, what happens is our application is going to go through all of the gap profiles, and it's going to use the UUIDs to identify what are the different services, and that's how it's going to determine where the different information goes in our app and our database. One great thing about this is that BLE is a low power mode, so we do have like a smaller battery, but it lasts very long. It didn't even die on us when we were using it, so it's a very like good thing for our project. Also, BLE sensors have been used sealed inside a shoe with no way to charge, and they like outlived the life of the shoe. Basically, BLE is very like effective and it's efficient like with energy, so that's very useful for our project. For our sensors, I want to talk more about instead of like the theory behind how they work, just the parameters we're going to use. Basically, so for infants, more so after 1 month, a healthy heart rate is from 80 to 130 beats per minute. If the infant is before a month, it can go up to, I believe, 170 and down to like 70. So it ranges, but for the most part, we're going to be looking at heart rate from 80 to 130 beats per minute. And basically, any irregularities that are detected, it's going to trigger an alert in the application. For our microphone, we already have it pre-processed, so like the application won't show any it won't show any like decibels or anything. It'll basically just show like a range of like the sound level, and the different sound levels will determine different things. Like if there's like a low sound level, maybe the baby's like turning over or moving. But if there's like a larger sound level and it's like more constant, like baby's obviously like under more stress, might be crying, something like that. And that's basically how we'll use different like sets of ranges for the microphone. As for like the thermometer, a healthy ambient temperature for an infant is from 68 degrees to 72 degrees Fahrenheit. Our sensors aren't 100% accurate. So we're gonna have some room for like error. So maybe like a couple degrees below that range and above it. Otherwise, that's basically what we're going to be looking at. Anything out of that range will send an alert as well, because it'll be some kind of stress that we don't want the environment to have. The accelerometer in our project is also gonna act similarly to our microphone. We didn't want to have like the app read like acceleration, so we have like basically like we pre-processed it, and there's a range, and basically if there's a low amount of movement, it'll say that, and if there's a large amount of movement, it'll also say that, and that'll also indicate different things. Like a lot of movement will probably be like a lot worse than like a little bit of movement, and that can be determined by how much movement there is and how long there is that movement. For our hardware design and implementation, we basically went through these 3 iterations. The first iteration was in the fall. We started with the Arduino Uno, and we had just our heart rate and oxygen sensor, and we also had a temperature sensor. And basically, we evolved from that to the Arduino Nano. It provided BLE, which we wanted to be able to use with our application, and it also provided a lot more storage, flash memory, and like overall storage, so we could run all of our code at the same time, because all the sensors have their own code and their own like libraries. So that was important. We needed more memory. And then in our third iteration, which was mostly towards like the end of the spring semester, we implemented a battery. So I don't know if you can see the pictures. They're not hooked up to the computer with that like white micro USB cord. It's hooked up just by the battery, and that's enough to keep it running for a good amount of time. So all our sensors, we have all the final designs in. Just now we're just working on the battery. So that's how far we've gotten with this so far.
For the PCB schematic circuit, this is it. Specific to note is the switch in order to further regulate the battery consumption, the voltage regulator to regulate the output voltage at 3.3 volts, which is what's acceptable for the microcontroller, and an LED to regulate to see if 3.3 volts is being outputted, and then if not, then the LED will turn off.
For our software design and implementation, this is basically what the application looks like using it like in an actual phone. Those are the 5 sensors, and then above it, it also has a description of the environment, if it's like stressful or if it's a healthy environment. This application, it's connected to our Firebase, which is basically our database through Google. Everything that is sent to the application from our Bluetooth is automatically sent to the database, and that's saved there. We wanted the application to be really simple, just because we thought that would help a lot with making it more like usable for just like regular people. We didn't want to make it too complicated. That's why like you can see the application, it looks pretty basic. We didn't want anything more than that. And this is our cloud database. As you can see, there's timestamps. That's for whenever the application was connected to the microcontroller. It automatically uploads it. And to the right of the timestamps, you can see it has heart rate, motion, oxygen, sound, temperature. Whenever those are, this wasn't with the, this was just a test, so that's why it only has the heart rate. But with everything running, it'll have all of the values to the right there. So it's actually very useful if you need to go back and take a look at any of the other values. So basically everything had, all the different sensors have their own like collection of data, and that's about it for our database.
For the hardware testing and analysis, testing charts were created for each sensor and circuit component. The sensors were initially tested individually and then once and then a new sensor was added every single time until all 5 were implemented. The hardware sensor code was altered to take an average in order to achieve more accurate result in outputting values less frequency. The power supply circuit was tested for both its length and viability in powering the entire microcontroller and all the sensors for extended periods. The battery was also tested for its ability to charge and discharge properly. For the sensor data analysis, the test shows that the data sensors perform as expected. Similar to the hardware test, the sensors were initially tested individually, and as shown in the graph, we can see that the temperature sensor does the sound and the total measurement were all measured together. The temperature was attempted to be changed in the third half, and the same was done for sound and movement in the second and third halves. For the software testing and analysis, the reliability in the BLE connection, the cloud-based the cloud database functionality and ease of use were main testing criteria. The app functionality was iteratively implemented and debugged based on the testing results. Changes in design and functionality of the application were made to meet our project goals and our defined requirements. And code updates were shared regularly using GitHub. In terms of BLE connection analysis, upon opening, the app is able to connect to the BLE peripheral in approximately 0.5 seconds on average. This allows for a seamless user experience upon entering the app. If the connection ever drops, it is programmed to immediately attempt to reconnect to avoid missing data. For the integration testing, it was performed for the application to integrate with the microcontroller and the cloud database. 5 iterations were required to fix bugs in the integration of the application and the microcontroller by improving the BLE service implementation and data processing in the app.
So to sum everything up, throughout this project, we've learned a lot, including having to research topics, new topics including Bluetooth Low Energy and cloud database design. And also throughout the process, we learned how to work in teams and how important communication is, and how important it is to split large tasks into smaller doable tasks, which can be done by each individual throughout time. And for our future work, we have 3 main things. One is to possibly improve the efficiency and decrease the size of the circuitry by instead using one unified PCB to hold everything, so it'd be very small and usable. 2 is to research more advanced data analysis algorithms, so the alert can be triggered earlier, so that would allow for earlier detection and earlier mitigation. And 3rd, to add an away mode to allow for alerts and autonomous mitigation when out of range with the device. For example, if you were to have a smart home connection and it could alter the temperature in the room or change different things like moving the blinds, etc. So here's our cost analysis. Overall, we just have our main sensors, the battery, PCB, and the microcontroller. The total cost comes out to $131 for everything altogether. And here's a quick demonstration of the project. You can see first, let me pause right there. There you see the microcontroller connected with the sensors and the battery. And upon opening the app loads up, it connects, and then it starts displaying the data values. And if you notice, he starts shaking it to try to alter shaking it and making noise to change the motion and sound, and they turn red to indicate an alert. And also, you see in the cloud database, everything is being uploaded in real time. So here are the standards and constraints. So for the standards, we had IEEE 802.15.4, which was used for our Bluetooth Low Energy implementation. Also ISO 14882, which was used for the C++ code for the microcontroller. The main constraints included the hardware size, which needed to be efficient and minimal to fit our main goals. Also, the microcontroller needed to have enough memory for the program to run, including transitioning to remote work and working as a team over Google Meet a lot. We held meetings weekly, and also dealing with time constraints. As for the ethics issues considered in our project, we went through every single IEEE Code of Ethics, and all of the terms are followed by our project. And one that is especially important to us is the 9th term, which is to avoid injuring others, which is extremely important because our main goal is to ensure an infant's health, not to injure anyone. And as for the complex problems that we ran into, project, fix all of them. Also, we need an efficient power supply. And another issue is that we had an insufficient of memory storage, so we had to get a new microcontroller with more storage. Additionally, we had to understand Android Studio, Arduino I, and BLE, and learn all those new ideas to complete the project. And one additional issue was that the Android BLE API is lower level than most others, so it was a little tricky to work with, which is why we had a lot of problems with the integration testing, but we got it to work. So references are attending.
Okay, thank you. Any questions? Okay. So let's welcome our last team. Grow My Data, Plant Environment Status Monitoring System. Roberto, Jason, Vito, and Alex.